this is what we were talking about this yesterday. So we had this, the estimation commands, and the only thing that I didn't cover there yet, and I'm not going to explain again how this exactly works, the empirical based estimates, that you need to get information about the deltas, which then feed into the level 2 models. In terms of the interpretation, I want to introduce sort of two ideas. One, the idea of a fixed effects interpretation, and then second, again, the idea of random effects interpretation. And for fixed effects, I will do in two different ways. I will talk about it in terms of the odds ratios, and then I will also talk about it in terms of predicted probabilities. And then when we get to the random effects interpretation, I'll do that with predicted probabilities. Again, most frequently, scholars really do this with fixed effects interpretation. And that makes things a little easier because you don't have to worry about these empirical based residuals. And in fact, until GLAM came around, it was actually extremely difficult to do anything else but fixed effects interpretation. That's what the GLAM allows you to do random effects as well. The odds ratio interpretation is based on the Logit, and Logit has the nice feature that it's a linear function. And that interpretation is relatively straightforward because of that, but when we get to predicted probabilities, things do become a little bit more complex because they are nonlinear functions. So let's start with the odds ratio bit. This is not working. Again, when we do it with models without cross-level interactions, or rather without any kind of interaction, we could say that that we have a model, say a random slope intercept model, that did I forget to switch it on somehow? That we have a random slope intercept model that looks like this. So we have the constant, the effect of the level 2 predictor, the effect of the level 1 predictor. We have an error associated with the intercept, and we have an error associated with the effect of x. And what we do in a fixed effects interpretation is basically always the following. We average over the level 1 and the level 2 units. And by averaging over the level 1 and the level 2 units, we actually get rid of all of the random components in this equation because in expectation, delta 0j is 0 and delta 1j is 0. So that means that all we have left then in expectation, or the expected logic, is gamma 0, 0 plus gamma 0, 1 zj plus gamma 1, 0 x ij. And that is then what we interpret. And actually what we then end up having is basically the same setup as what we have in a single level logic model, because there's nothing different anymore compared to that model. And therefore we can actually do the interpretation analogously. And of course, the logit is the natural logarithm of the odds. And if we want to turn it in terms of a odds, then we have to exponentiate. And so what we would then have is for the odds for individual I in context J, or rather the expected odds, we have gamma 0, 0 plus gamma 0, 1, zj plus gamma 1, 0, xij. And now imagine that we then do the following. We say, let's change, say, the x variable. Let's increase the x by 1 unit while keeping the z constant. Then you can actually evaluate this odds for the new value of x. You can compare it to the odds for the old value of x. And it turns out that when you take the ratio of those two odds, you end up having something really straightforward, which is that the factor change in the odds due to x is simply e raised to the power gamma 1, 0, just the coefficient that's associated with the predictor that you're changing. And of course, if you were to change z while keeping x constant, then it would be e raised to the power gamma 0, 1, which that happens to be the coefficient associated with your predictor z. And so it's a fairly straightforward mode of interpretation, especially when there are no interactions. So if we sort of go back to this example of voting for Labor in the 2001 elections, we had these predictors, Labor identifier, which is a 0, 1 predictor, 0 if you don't, 1 if you do identify with Labor. Ideological distance, which ranges from 0 to 10. 0 if your position coincides with Labor's position on the left-right scale. 10 if you basically see yourself at the opposite end of the ideological spectrum from Labor. And then 2 class variables, middle class, working class. 2 because the baseline category here is people who don't identify with class. And then this is just repeating the estimates that we had earlier from the random intercept model. And then we can turn those estimates into factor changes very straightforwardly. In fact, we don't actually have to do anything by hand, because you can estimate this model in GLAM, calculating the coefficients gamma, and then you can issue afterwards the command GLAM, E form, and then it reports the same results back to you that know as factor changes in loss. And so how do you interpret that? Well, this Labor identifier has this enormous factor change associated with it, but it's not so surprising. It suggests that compared to people who don't identify with the Labor Party, the odds of people who do identify with the Labor Party or voting for that party are 89 times higher. And the question is whether this is not just endogenous to vote choice, but let's assume it's not. So 89 times higher odds. Very important. It's the change in the odds. It's not the change in the probability of voting for Labor. It's the ratio of the probability of voting for Labor over the probability of not voting for Labor that changes. Ideological distance, which has a negative coefficient, should be producing a factor change that is that is less than 1 because of that. And yeah, I don't understand.
It's lighting up.
Yeah,
Sorry, and
I'll just play with it after
Okay,
I'm done with
sorry.
these slides. No problem. So it has a negative coefficient, which means that the factor change is going to come out less than 1, which means this ideological distance, of course, means that if you increase the ideological distance, you move it away from labor on the left-right scale. So the odds of going through labor should shrink, and that's exactly what this point A says. In fact, if you were to convert that into a percentage, and sometimes people do, you just subtract 1 from 0.8 and then multiply times 100. And that means that the odds shrink by 10% for each unit change in the ideological distance. Similarly, interpret this middle class and working class. Now, these odds, these factor changes, the way I've reported them here, are point estimates because they're basically the factor change formula is something that you have to estimate based on the fixed effect estimate, the gamma estimate. And so it's sometimes useful to actually also get confidence intervals on the odds ratios and on the factor changes rather. And this we can actually do fairly straightforwardly because when we look at the effect of the covariant itself on the logit, that effect has a 95% confidence interval that is equal to the estimate plus or minus some critical value C, which happens to be 1.96, times the standard error of the estimate. And to actually turn that into a confidence interval for the odd factor change, basically you use something known as endpoint transformation. So you take the endpoints of this interval and you just plug them into this formula for the exponential. So that e raised to the power gamma equals to minus 1.96 times the standard error as the lower bound, and as the upper bound e raised to the power gamma plus 1.96 times the standard error. And that's what I've depicted here. So you see actually that some of these confidence intervals on these confidence intervals tend to be fairly large. The labor identifier, well, you see the effect is always enormous in terms of factor change. There are also a couple that are interesting when you look at the estimates for the factor changes for middle class and working class. You see that if you look at the 95% confidence intervals, the value of 1 is included in those 95% confidence intervals. Which essentially means that the factor changes are not statistically significant at the 0.05 level, but that is no different than what you would have observed from the set of estimates. There you would find that middle class is statistically significant at the 0.10 level, but not 0.05, and that working class is not all significant. Now, how do we interpret models that have interactions, for example, a cross-level interaction? Again, what we do is we work with the expected logit. So, the expectation over the logit, which means essentially, again, we wipe out all the random components. In a sense, what we're doing is we're sort of saying, for some unit whose effect, whose intercept is exactly the average intercept, and whose slope is exactly average slope. What is the effect of, say, predictor X? And here we can do something very similar to doing simple slopes, which we did with the hierarchical linear model yesterday. So if we want to look at the expected effect of X, rather the effect of X on the expected logit, what we take is the partial derivative of the expected logit with respect to X. And what we then are left with is the statistical main effect of X plus the interaction effect times the value of Z, which is then the moderator. This is what changes the effect of X on the expected logit. You could do, of course, the same with respect to the level 2 covariate. That's what I've depicted here in the model. And this is then something that you can actually calculate fairly easily as well. So we modify the model a little bit to bring in an cross-level interaction. So the previous model was just a random intercept model, which had only level 1 covariance in it. Now what I'm going to do is create a random intercept and slope model that has additional and that has also level 2 covariance. So the model for the level 1 model is essentially the same as what I had before, the same predictors that is, but we now let the intercept vary as a function of labor's vote share in the district in 2001. And we have a level 1 error term delta 0. And I'm going to let the effect of identification with labor vary also across the contexts, the polling districts, again as a function of labor's vote share and the random component delta. All of the other ones here, ideological distance belonging to the middle class, belonging to the working class, I have constrained to be fixed. So this then effectively is the model that we get, the mixed model. We substitute these equations here in the stop equation. We take the expected logit, which means we can get rid of the last 2 terms, and then work with it. So here are the estimation results that we get. We see, of course, not surprisingly, that labor vote share in the district has a significant beta effect, and the interaction between the labor identifier and the labor vote share is marginally significant. It looks like this ratio is 2, but that's a bit rounding. It's the p-value is just slightly above 0.05. So now we want to actually deal with this interaction effect. And what we're going to do now is using again this Lincoln command that I discussed yesterday briefly to answer a question. That is, imagine I want to know the effect of identification with labor on the logit when the labor vote share is 50% in the district. And instead you can do that by typing Lincoln lab ID. That's just basically picking up the coefficient associated with lab labor identification, plus the interaction coefficient times the value of Z, which in this case is set to 50. Then the resulting slope estimate is 4.58. That's the effect on the logit with a standard error of 0.25. And if you want to now say, well, that's the effect on the Logit, and what's the effect on the odds, then the only thing you would have to do is compute e raised to the power 4.58, and you would have that result. Now, this interpretation in terms of logits and in terms of odds ratios is by far the easiest way to interpret things, but it's not necessarily an easiest way in a sense that technically speaking is very easy to do. But it's not necessarily intuitive in the sense that it's easy to interpret what you get. In some ways, I like to think about predictive probabilities much better. I can wrap my brain around predictive probability much more easily than around an odds ratio. And it's always, I always say with the interpretation of these models, do whatever you feel comfortable with. As long as you do it right, of course. But I have not met many people who feel really comfortable interpreting odds ratios. So, and I certainly am not one of these people who think naturally in terms of odds. I guess I'm not a betting man, and that's sort of the issue that it's not intuitive to me. There are disciplines where it's sort of dictated how you interpret things. Like medicine, everybody works with odds in medicine. But in political science, there is not such a tradition, so pick whichever you find appealing. I like to work much better with predictive probabilities, and so that's what I will turn to next. But it is easy to make mistakes calculating predictive probabilities in multi-level models. So I will show you how it's done, and also show you how you should not do it. And I have to admit that the way you should not do it is actually a way that I've once used. So also fallen prone to this mistake. There are actually two kinds of predictive probabilities that you can calculate. One where you can say they're based only on fixed effects, and one where you explicitly take random effects into consideration. Now, they go under a variety of names. I find none of them appealing, these names, but the one that seems to make most sense to me is marginal predicted probabilities versus conditional predicted probabilities, where I should immediately say, if you've ever dealt with marginal effects as a way of interpreting logic models, be careful. Marginal predicted probabilities are not marginal effects. The marginal effect is the change in the predicted probability when a predictor changes by an infinitesimally small amount. Economists like to use that for implementation. That's not what I'm talking about here. The term marginal doesn't refer to marginal effect here. It refers to how we deal with the random components. And what we're doing is, in a sense, obtaining a marginal distribution, just the way you would obtain a marginal distribution in any probability setting, that is by integrating out the other source of variation in the one that you're interested in. In this case, what you're integrating out, because you're only wanting to look at the fixed effects, is you're integrating out the random effects. And that's important to remember. So this is a bit the equivalent of a fixed effects interpretation in a hierarchical linear model, but computationally you get to that interpretation by integrating out the random effects. Then there are conditional predicted probabilities, which actually allow you to focus on random effects. And so you're not integrating out the random effects because you want to explicitly consider them. And why we call these conditional is in a sense you're saying, well, given a particular value of the random effect, what is the predicted probability of volume for labor? That's why we call it conditional. Now, start with the marginal predicted probabilities. And this is how you would calculate them. So you would take all of the random coefficients that are out there, and you would integrate them out by basically relying on the fact that they have a multivariate normal distribution. Now, this is the right way to do it. What sometimes is done, but what is actually wrong, this is the thing that I fall prey to as well, is to say, well, let's just set the deltas equal to 0 and then calculate the probability. But that doesn't work because actually what we want is the average of the inverse Logit. And that is not the same as the inverse of the Logit of the average. So this is the right way of doing it. Don't do this other thing. And fortunately, we don't have to really worry about doing this integral at all, because one of the nice things about adaptive quadrature is that it evaluates these integrals anyway, so you can actually pick them up pretty easily. So in GLAM, what you would do is you would type GLA-pred, that's the command for getting predicted quantities after you've done the estimation, to give it a name, and then mu, because you're in a sense asking for the mean of the dependent variable, which for a binomial distribution happens to be the probability of scoring 1, that's what you're getting. And then, importantly, you have to type marginal to obtain this marginal predicted probability. So, if we go back to the random intercept model, so we're abandoning all the stuff we did before, so we just go back to this model. Say I'm interested in the effect, in plotting the effect of ideological distance on the probability of volume for labor. Then I would have to set some values for the other predictors. So I decided to say lab ID is 0, people don't identify with the Labor Party, and I'm looking at middle class voters here. And then here is what you get as the finite marginal predicted probability of the labor vote as a function of ideological distance. When you see when the ideological distance is 0, the probability of voting for labor is close to 1, and it drops to basically almost 0. No, actually it's not right. You do the scale wrong. It's 0.1, and it drops to about 0 when you get to maximum ideological distance. But it's not possible, as best as I can tell at the moment, unless you do simulations, is to get a confidence interval around this line. So that's a bit of a downside. But that is something that well, people might want to see that tells you a bit about what is going on.
And we will be using the clarify routine after the GLAM commands? Or?
Clarify does not work with GLAM. GLAM does have its own simulation routine, so you can use that, but clarify doesn't work. And I don't think, I mean, usually I actually try to calculate standard errors analytically. I don't think you can do that in this case. Math just gets too complicated. Again, this kind of picture is what I would show for the implementation. I would say, look, this is the effect of ideological distance, and rather than to describe that with unloading, it's certainly not enough to just show the table of the results. I would at least describe what better graphically represented. Let's talk about conditional predicted probabilities, and these are actually relatively easy to calculate because they are just based on a particular value of the random effects. You can just evaluate the probability by just substituting that value of delta. And you can do that in Stata as well, and it goes exactly the same way as it did for the marginal predicted probabilities, except you don't include the option margin. And then what you get is actually the possibility of depicting the relationship between, say, ideological distance and the probability of the labor vote. You have the opportunity to depict that for various levels of the, say, the variance of the error component associated with the intercept. And you could also say, well, let's pick a particular polling district, take its value for delta, and then take that into consideration when computing the predicted probabilities. So here I have actually done this for 3 polling districts. Here's ideological distance, and here are then the effects of ideological distance on probability of falling for labor. And so we have Angus here, we have Merriman here, we have Wrexham here. And they show you a little bit that these predicted probabilities seem to respond a bit differently to the ideological distance. That is even though I did not interact ideological distance with anything here. And that's the thing that you may recall from logic and problem models, is that predicted probabilities are always conditional in a sense. It always depends on what the rest of the terms in the model look like, and that's what's being picked up here. You'll notice that some of these lines are very short, and one of them is longer. And that just has to do with the fact that, for example, in Angus, we didn't have any respondents with an ideological distance to labor greater than 2. That was it. Whereas in Meriden, we actually had nobody who was really very close to labor. The least distance we had there was 2, and it went all the way to people saying, well, I'm the opposite end of the scale as labor. So that's being picked up here empirically as well. And that's what it should be. I mean, you should really not be extrapolating these lines to territory where there are absolutely no data points anymore. So this is actually the right way to depict it. Now, I just did this for 3 districts. Of course, there are 127. I did not bother to put them all in. It would be basically, maybe it would have some artistic value what you get out of that, but in terms of interpretation, it would not help a great deal. So if you want to depict everything for every district, then probably the best thing to do is to plot out like I did earlier, where you list the districts and then you show the empirical base residuals. That would be a better strategy, but this kind of plot I would use to actually just depict some interesting cases to show what the range of things is. So, I mean, one strategy you might even want to use to depict this, which is not what I did here, is to take, for example, the smallest random component, the largest random component, the 25th percentile, the median, and the 75th percentile, and depict those 5 cases.